If a particle feels both a static potential and a fast, high-frequency oscillating force, its motion splits into two parts, a slow average motion x plus a small fast jitter 11. The fast jitter is fixed directly by the high-frequency force. M times the second derivative of 11 equals that force, giving 11 equals minus F over m²², a small amplitude. Averaging the equation over the fast oscillation, the slow motion x behaves as if it moves in an effective potential. This effective potential is the original one plus a correction proportional to the squared amplitude of the oscillating force. Applying this to Kapitza's pendulum, we vibrate the pivot up and down at high frequency, and the effective potential gains a term proportional to sin²θ. If the vibration is fast and strong enough that a²ω² exceeds 2 GL, a new minimum appears at the top. The inverted position becomes stable. So a rapid vibration can be described by an effective potential. That is exactly what lets Kapitza's pendulum balance upside down at the very top.